Hello. In this video, we'll just continue with Unit 1 concepts that you will need to go through the past papers that we will hopefully solve once we're done with the theory. So, what do we mean by adding forces, and also where do we need this? So, this is useful when working with free body diagrams. Okay. So, I broke things up into cases. So let's start with the first case, okay? Which is when the forces align in a straight line. So straight lines. Okay. So let's say that you have this force F1 points to the right or the positive x direction, and its magnitude is 5 newtons. And then you have another one, F2, which has a magnitude of 10 newtons. If you add them up, F1 plus F2, you just line them up since they're in the same direction and add them up in a way that they scale. So, I mean, it's not, the way I drew them, they don't appear to be in scale, but you get the idea. Like if this is 5 newtons, then F2 is twice as large as F1. Therefore, F1 plus F2 is 15 newtons, which is 3 times as large as F1. Okay, so you just add them up. And the same goes, of course, if they are, I don't know, you have F3 is 1 newton and F4 is 5 newtons. They both, point up in the positive y direction. So you add them up. If you want to add them up, you just add the magnitudes and you get 6 newtons also pointing up, right? Simplest case. Second case, the vectors are perpendicular. Sorry, I said vectors because force is a vector quantity, but the forces, okay, the forces are perpendicular to each other. Okay, how do you add them up? Let's say that you have F1 points to the right and F2 points up. Here I'm drawing the vectors, okay? That's why here we don't use the arrow because we are dealing with the magnitudes of the vectors. So here we just draw the vectors, okay? So vectors have, again, direction and magnitude, okay? So to add them up, you connect the tail of the first one with the head of the second one. So this is the force. So that's sigma F, okay? And if this angle is theta, okay, then the magnitude of sigma F, which we write without the arrow, okay, the magnitude is just the square root of F1 squared plus F2 squared, where F1 and F2 are the magnitudes of the vectors F1 and F2, okay? So yes, and this will be newtons, and this is the magnitude. And how about the direction? Oh, and this is the Pythagorean theorem pretty much, because the two vectors are perpendicular to each other, okay? That's why we use the square root and then we sum the components, okay? Not the components, the magnitudes, I'm sorry. So the direction is, we can find it by finding the tangent of theta, which is simply the magnitude of F2 divided by the magnitude of F1, okay? And as a simple example, let's say that I have a force 110 newtons to the right and 70 newtons up, okay? So the direction is immediately this one, okay? So that's the direction. It points, what is it? Northeast, right? Yes. So sigma F is the square root of 110 squared plus 70 squared, which is 130 newtons, okay? And the tangent of theta is 70 over 110, which yields an angle of 32 degrees, okay? So the direction of this resultant force, okay, is 32 degrees with respect to the horizontal. This is how things are expressed, okay? Or you can also say, okay, this is the horizontal. Actually, let me use a different color. Okay, this is good too. These are some good concepts to be aware of. So this is the horizontal. So this angle is 32 degrees. But you can also equivalently say that it's, what is it? 58 plus 32 gives me 90. Yeah, so you can also say that this force is 58 degrees with respect to the vertical. Okay, they are both equivalent. Okay. Okay. Now let's do the third case, and I think it's the last case. Yes. So the third case is when they are non-perpendicular forces. Okay. So maybe F1 looks like this, and maybe F2 looks like this. Okay. So the first way to add them is to connect the start of F1 to the end of F2. Okay, so let's see it. So let me draw it again. So this is the F1 vector, the F2 vector, okay, and sigma F. So this is the start, this is the end. So that's sigma F. Okay, and this is the direction, and this is the angle. Okay, so actually this angle gives you the direction. Okay, and let me see. What else do I want to add here? Okay, a reasonable question is, you might ask me, okay, how do you find that angle theta? So to find it, you need to, okay, this is a right angle. Okay, so if this is, say, equal to A, and this is, say, equal to B, let's say that they give you these vectors at the scale, and you can use a graph paper or something like that. So tangent of theta is simply A over B, and it can be calculated if A and B are known, or actually known or given, or if F1 and F2 are given at the scale. Okay, which means you can use your ruler to measure, literally measure A and B. Okay, so you will need a ruler or a protractor, right? Because if they tell you it's at the scale, you can just actually there is a ruler here, we used it before. Okay, so maybe you have a ruler and then you measure this angle. Okay, it's 24 degrees, say, I don't know, less than that actually, 218 degrees, something like that. Okay, right. The second way to add non-perpendicular or parallel vectors is the parallelogram rule. Okay, so that's the second way. The parallelogram. That's a mouthful. Parallelogram rule. Okay, now in actual Greek, this is a Greek word. Parallel means, okay, parallel. And gram, what does it mean? It comes from grammi, which means line. Okay, so parallel lines, this is what it really means. Okay, so See, even Greeks forget they are Greek. It sounds ridiculous. Anyway, so F1 and F2, okay? So the parallelogram rule tells you that you need to draw parallel lines. So a parallel to F2 and then a parallel to F1, all right? And the summation is the diagonal, okay? So this is the diagonal, okay? So is there anything else to say here? No, that's it. And actually we don't say it directly, but you actually use the parallelogram. Okay, sorry. You use the parallelogram rule when you add perpendicular vectors as well, because notice that I can draw parallel lines. And this is just a diagonal of this rectangle, okay? And a rectangle is a special case of a parallelogram, correct? So, yeah. All right. And to measure the angle, again, so let's say they ask you to find this angle, you need graph paper and protractors and rulers and so on, okay? Okay. So as I said in the beginning, this is useful when you deal with free body diagrams, okay? So let's see what I mean by that. So free body diagram. Okay, so maybe you have an incline, and then maybe you have a box of some sort, okay? So how many forces are acting on this thing? The weight, m times g, the vertical force, n from the floor, and then maybe you have friction. Actually, it's along the floor here usually, but okay, let's draw it there. So that's the friction. And by free body diagram, we mean that we remove the body and we remove everything and we just draw the forces like this. Okay, mg, f, and n. Oops. That's n. Okay. So I don't know about what they might ask you in a past paper, but you can use graph paper and use the methods we discussed here to calculate things that they ask you about these three forces, for example, okay? So this is it for vectors and such. Sorry, for forces, for adding forces. And before we move on, I want to mention that any vectors, not just forces, but maybe velocities, etc., can be added using the methods discussed here. Okay, right. Let me check. As I mentioned a billion times, I have two sets of notes with me. Which I use to make sure that that I am discussing things properly. Okay, so let's move on to the next topic, which is moments. Okay, and there are many tricky problems that Edexcel gives to students related to moments, but hopefully the presentation will be clear and help you to go through this problem. So if we exert, so let's define what a moment is. So if we exert a force on an object at a distance x from some pivot point, oops, not moment, point, okay, the object will turn, oops, the object will turn, So let's say I have a pivot point. Okay, that's my pivot. And I have some rod, okay, that can rotate around this pivot, okay, and I exert the force F downwards at the distance x from the pivot. Then the moment, okay, first of all, the rod is gonna turn, what is this, clockwise, right? And the moment will be equal to F times x, and we use units of newtons times meters. And for those of you who are into cars and Formula One and these kind of things, this is the unit they use. They call it torque, and it is used to express how strong an engine of a car is, because the engine turns and kind of gives torque and power, and speed to a car. But okay, I don't want to confuse you. So, and also here it's a clockwise moment. Okay. And you can also have a counterclockwise moment, okay? How can you achieve that? So this is the same rod as before, okay? And maybe you exert the force in the opposite direction, so this is gonna make it turn this way, right? So the moment is again, actually I'm gonna write it in parentheses, it's actually minus F times X, but we will get to that later, so. Okay, so F times X, you can say counterclockwise, and this accounts for the negative sign, okay? All right, and it is implied that, okay, if I exert the force here at the distance of x over 2, then the moment is going to be F times x over 2. And as I move closer, okay, if I exert the force at the pivot, there is no moment, okay? So for this situation, the moment is 0 because the distance from the pivot is 0 pretty much, okay? We are exerting a force on the pivot. So imagine yourself pushing the door from the pivot point. I mean, it's not gonna move, okay? So something like that. All right. Next is the principle of moments, okay? So principle of moments. Okay, which tells you that if the sum of all clockwise moments is equal to the sum of all counterclockwise moments, okay, we have equilibrium, which means that the object will not turn pretty much, okay? So, so let's see an example. I have a pivot point in somewhere along a road, okay? Doesn't matter where. And maybe I'm exerting a force F3, okay, which wants to turn the object clockwise, okay? Let me think. Counterclockwise. No, that's clockwise. Okay, this pushes up, so it wants to turn it clockwise. And then maybe I have a force on this side. Okay, let's call it F1. And this distance is x3. Okay, and then I have a force F3 at the distance x1. Okay, that wants to turn the object counterclockwise. Okay, and then maybe I have another force F2. Okay, which give me a second, I need to correct something. Okay, and then I have a force F2 at the distance x2, which also wants to turn the object clockwise, okay? Then to have equilibrium, we need we need the sum of all clockwise moments, which is f3 times x3 plus f2 x2. Okay, so what is it? f3 x3 plus f2 x2 must equal f1 x1, which wants to turn the object counterclockwise. f1 x1. So if this is not true, the object will turn. Okay. All right. Is there anything else I want to talk about when we discuss moments? Let me think. Okay, another thing is what happens when we have a force at an angle. So force at an angle. So let's say we have again a pivot, and the force actually looks like this. Okay, and maybe they give you this angle as theta. Okay, this is the force F. Okay, this force F, okay, can be analyzed. Remember, you can parallel transport vectors, kind of. I mean, you're free to do that. So you can transport this F. I mean, if it's difficult for you to understand, you can picture it as being moved over there, okay? So if this is theta, this is also theta, and therefore you have a force F sine theta, a component of the force F sine theta, and another component F cosine theta, right? Because you can analyze this force into force perpendicular to the rod and parallel to the rod, okay? So the moment in this case is going to be F cosine theta times X, where X is this thing, okay? Is this distance. F sine theta is not perpendicular to the rod. Thus, the moment it exerts is 0, okay? So for any force that is not perpendicular to a rod or to an object that has a pivot point, etc., the moment is 0, okay? That's a really important thing to have in mind. Right. Okay. When we discuss moments, very central to the concept of a moment is the center of gravity of objects, okay? So let's discuss this briefly. Center of gravity for objects. Okay, so this is found, so in general, the center of gravity, coincides with the geometric center of objects. Okay, and because I want to have my consciousness clear, okay, I need to specify that this is only true for objects that have a constant density, okay? So for constant density. So a rod that consists of the same material, for example, okay? Because there are objects that don't have a constant density throughout, okay? So the center of gravity will be different. But for AS-level physics, 99.99999% of the cases, the center of gravity will coincide with the geometric center. What is the geometric center? For example, if I have a circle, the center of gravity is the center of the circle, which is the geometric center, right? If I am dealing with a square, okay, then I draw the two diagonals. That's the geometric center, and it's also the center of gravity. Okay. What's so important about it? about the center of gravity, the weight of the object, okay, appears to act from the center of gravity. Okay, so okay, let's see where that becomes significant. So let's say that I have, okay, maybe I have an object that is kind of rectangular, and that's the center of gravity. So this is a high center of gravity, let's call it like that, okay? But if the same object is turned on its side like this, now I have a low center of gravity, okay? So objects are stable as long as the center of gravity is above its base, okay? So the base is this one in this case, and this is the base in this case. But if, for example, I put the same object on an incline, okay, and okay, this is the center. Oops, I don't know why it does that. If you know why my iPad does that, let me know in the comments, okay? But in this case, this is the base, and this is the center of gravity, okay? The center of gravity in this case is not above the base. So center of gravity not above the base, okay? In other words, I mean, remember the weight? We said that the weight of the object appears to act from the center of gravity. So in this case, the weight is perpendicular to the base pretty much, okay? But in this case, it's not, okay? So it creates a torque, okay? And maybe the object will topple, will fall, okay? This is the significance of the center of gravity, all right? And we will hopefully see some examples through the past papers. Okay, is there anything else? I have a really nice example in my second set of notes about the center of gravity. So let me tell you that, for example, okay, so these are kind of regular objects, meaning that they consist of the same material. They have a symmetrical shape and stuff. So you can talk about the center of mass being at the center of at the geometric center of the object. But okay, what happens if we have irregular objects? Irregular. So a hammer, for example, okay? So a hammer consists of a really heavy head, okay, which is made of iron usually, or steel, I don't know, something like that. So this is a hammer head, okay? So the center of gravity of this object, of the hammerhead, is at the geometric center of this rectangle, but it also consists of a wooden part, okay? Let's draw it with orange, okay? So the center of gravity, if we remove, I mean, if we remove, oops, I cannot do that. So what I'm trying to say is that if we remove the hammerhead, okay, then, oops, I need to go back to this, then the wooden part will have a center of gravity somewhere there, okay? But for the composite object, the hammer, the center of gravity is closer to the larger mass. So the center of gravity will be somewhere here, for example, okay? So the center of gravity for irregular objects will be closer to the larger mass, which kind of makes sense, right? And to find it, you need to balance it on something, okay? So it depends on the case, so I'm not going to discuss it extensively. Instead, I'm going to solve an example, and then I'm going to stop this video, I think, because then the next topic is Newton's laws of motion, so I want to discuss those later. So in a different video, I mean. So let's see an example. So so two brackets A, B support a shelf of length, 1.2 meters, okay? So two buckets, I'm sorry, not brackets. I was wondering, that's why I was hesitating. So, okay, two buckets A and B support a shelf of L equal to 1.2 meters. So A is 0.15 meters from the left end, and a book is placed 0.35 meters from the 0.35 meters from the left end. Okay, so A, the normal forces of each bucket are equal. WB is 8.5 newtons and W shelf is 14 newtons. What is the distance of B from the left end? From the left end, okay? And I owe you a scheme. I'm sorry, I should have done that first. I'm sorry. So this is the situation. We have A over here and bucket B over here. So this is a book. Let's draw it with a different color. Okay, that's the book, and it exerts some force. Okay, and this is the center of this thing. Okay, and there is a weight downwards, and then we have the two reaction forces up. Okay, from the buckets. This is 0.15 meters, and the book is at 0.35 meters. 0.35 meters. Okay, and the whole rod is 1.2. The shelf, I'm sorry, not the rod. 1.2 meters. Okay, so how do we solve this thing? Okay, first of all, we need to work with the forces. Okay, so for the forces to have balance, we need 2 times the reaction force. We need that to be equal to the weight of the book plus the weight of the shelf, which together sum to 20. Let me see. 14 plus 8.5, that's 22.5. So 22.5 newtons. So N is simply 11.25 newtons. Okay, so that's the reaction force. And now we have to use the principle of moments. And we will apply it about the left end. And this is something I haven't mentioned. So we will apply the principle of moments from this pivot. But we can use any other pivot we want. We can use this one, or this one, or the center of the rod, or here, or whatever, okay? So you can get creative about which pivot to choose when you use the principle of moments. And usually you choose one that makes the most sense for the problem, or it eliminates some force that you don't know about, and stuff like that. So anyway, if we apply it from the left end, we have These forces want to turn it counterclockwise, whereas the force from the book and the shelf itself want to turn it clockwise. Okay, so we have to balance those moments. So n times 0.15 plus n times lb, and lb is what we are trying to find, mind you. Okay, so the distance from the left end. Okay, plus n times lb must be equal to WB times 0.35 plus W shelf times 0.6, because the center, how do we know that it's 0.6? Because the center of gravity for the shelf is at the center, is at the geometric center, right? So LB, since I use green, let's use green, is going to be WB times 0.35 plus W shelf times 0.6 minus n times 0.15 over n. Okay, and this ends up being equal to 0.86 meters. Okay, and that's the answer. And okay, as I said, I don't want to continue this video because it gets into topics that are a little bit irrelevant to moments and such. So I'm gonna stop this video here, and I also have to go. That's the other thing. And I hope that this video will be useful to someone. Please let me know what you think about these videos in the comments. Make suggestions, ask questions, let your friends know, like, subscribe, tell other people to subscribe, and so on. Thank you guys. See you in the next one.